Hey everybody, welcome back. Mr. Smith here. In today's screencast, we're going to give you all the basic skills that you need to have on you so that you can use graphs to study constant motion situation. So we begin by using position graphs, but before we even get to position graphs, we have to hit one thing that's a really big issue in physics and can make physics really tricky to deal with, trickier than maybe any other science you've seen before. And that is that in physics, we use language that you have heard of before, except that the definitions of the words might be different than what you actually are carrying around in your mind. And so, what you're going to need to do throughout the year in physics is think about the definitions that you're bringing when we present new material in class, and ask yourself, is this really what I have learned before? And if it is, maybe I need to be alert to changing it. So, what I want to do is show you something. There's a simple word, origin. When most people think of the word origin, they think of this first definition, which I pulled up from Webster's. It's the place where you begin. Everyone has an origin, the place they started their lives. They have an origin where they start their day. That's not what origin means in physics. The second thing, people think of math class, and they think that origin means 0, 0, where the x and y axis meet. And that's not what the word origin means in physics. And I'll show you what it does mean as we go through these examples. In physics, the word origin is a physical place. It's the place that you have to have in a room that you're going to measure everything else from. And maybe what we do on planet Earth is that we use Greenwich, England, as the zero of, I think, latitude when we measure out. And we give things a physical location. But anyway, what we're going to do here is just bring up an old concept that you've seen it for a lot of years. It's the number line. And I want you to notice a couple things about this number line example. To begin with, we've got a plus side of the number line and a minus side of the number line. And there's something that's subtle about this. This right here, according to our definition, this spot right here, I'm trying to point to 0, is the origin. It's going to be the 0 of position. And if I move in this direction from the origin, I'm moving in the positive direction. If I move in this direction, I'm moving in the negative direction. You also notice that it's got positive and negative territory. So I have positive positions and I have negative positions. Let's just do a couple of quick examples. If I had, let's say a position of right here and a position of right there, and that was position 1 and that was position 2. If I moved from this one to this one, I'm moving in the minus direction. But I could have a position here and a position here and make that same move, and I'm still moving in the minus direction. Okay? A couple of other little things. Here I'm moving towards the origin, and here you might notice I'm moving away from the origin. So there's a lot of ways that that word origin works its way into our conversations, and so be alert to it. You're going to want to ask questions about it when we get together in class. So we'll show you something else about how it works. So in this one, if we take our first position, to pick one, and say we're starting at negative 10 meters, and we'll take position 2 and run him out here and say he's equal to negative 25 meters. Let's follow the recipe and see what happens. We'll use delta. Remember, that means change in. Also, be careful when we use signed numbers that we do it right. So position 2 minus position 1 looks like this. We're going to take negative 25 meters minus a negative 10 meters, and we'll follow the recipe of adding signed or subtracting signed numbers, which is that subtracting equals adding the opposite. Anyway, when we're all done, we get that the change in position is equal to a negative 15 meters. So what we did was we moved 15 meters in the minus direction. So notice we're moving away from the origin, but we're in negative territory and we're moving the negative direction. So let's do something different then. In our second example, let's say we started at P1 again, same starting place, but we moved here for our second position. So let's go ahead and write it down. We'll follow our recipe. Delta position is thing 2 minus thing 1, and we'll pay attention to signed numbers like we did. So position 2 here is plus 5 meters, so he was in positive territory. We'll minus the initial position of negative 10 meters, do the right thing, which is add the opposite. And we can see here that you get a positive 15 meters for the displacement. So again, that's two things. This is telling us that we moved, in this case, in the positive direction, a distance of 15 meters. Where in the first example, we moved that 15 meters in the minus direction. Okay, so plus direction, usually to the right, minus direction, usually to the left. Okay? The next example you're going to like because it's really super straightforward. If you go to all the trouble of getting displacement and you go change in position is, I don't know, let's say it's minus 15 meters. If the question then asks you what's the distance, well, it's super easy to figure out because all you do is just put this guy in absolute value symbol, and that equals plain old positive 15 meters. So here's the logical idea with distance. That is an everyday word that really means the same thing as what we use in physics. Distance is how far did you go, and you don't care about the direction. And so that's why the absolute value, you just rip off the minus, you don't care about the plus. It's just the number part of how far did you go when you're talking about distance. Okay? So what we're going to do right now is put that on a graph and talk about a fourth idea in this presentation, which is that the slope of a position time graph is super important. And what we're doing may look a little tricky actually. By putting this on a graph, we've got now time on the x-axis, and we've now put our number line on the y-axis. So you're going to see motion to the right or to the left really represented as like an up and down motion here on the graph. So what I see if I just focus on the y-axis in this example is position 1 is 2 meters. So I started when time was 0, I was standing at a position of 2 meters. When I finished this little problem, looks like 4 seconds later, I finished at a position of 10 meters. So position 2 is equal to 10 meters. And I'm going to use that in just a second. When they asked me to get the slope of this line, I remember that slope is equal to rise over run, and so what I'm going to do is I'm going to go get the rise of the line, and I'm going to remember that that's equal to y2 minus y1. Well, you're going to notice that it's equal to the displacement. It's the change in position. So it's position 2, 10 meters, minus position 1, 2 meters, and I'll write that down in a second, but that looks like it's 8 meters, okay? What do I want to do right now is just go and get the run of the line, and over the length of time of this line segment happening, it looked like 4 seconds happen. And so the slope of this is going to be pretty easy to get. It's going to be 8 meters over 4 seconds, and easy enough to figure out. But I want you to notice something. The slope of this line, when we go and do the math, is 2 meters per second. So it had a positive slope, didn't it? Did you know? I don't know if you noticed it, but the line was slanted upward. So as time went by, the position was going up. That meant you were moving in the plus direction, right? Okay. So we'll practice with that. A related idea that we want to work on this topic of slope is, let's just say we had another line segment right here that was segment B. So if you want to get the slope of that, position 1 this time now is going to be 10 meters. And sometime later, we go down to here and then we zip across and look at the y-axis. And that tells us position 2 was equal to 4 meters. And it looks like that whole section of graph started at 4 seconds, 5, 6, 7, 8. So if I make another line segment here, a little sloppy, and I do this, then the rise is this much of a drop right here, and the run is this. Well, the run is easy. The run is 4 seconds, just like the last example was. But the rise, it's still going to be the change in position. So change in position, let's do it over here, is going to be equal to position 2 minus position 1. And this is going to make sense now. You were moving in the minus position, and there you go. That shows you the line was dropping. You were heading in the negative direction. And so if I put all this together and I go and figure out the slope, what it's going to tell me, again, is the velocity of this object. So negative 6 meters over 4 seconds, and my velocity during this time was negative 1.5 meters per second. Okay? Now, almost home free with this, there's another final related idea that you're going to really like, where distance was sort of like a simpler version of displacement. Speed is our everyday simpler version of velocity, and it really works the same way. If I had the velocity of this section, was equal to plus 2 meters per second, then the speed of that is just 2 meters per second. If the velocity over the section over here was negative 1.5 meters per second, then the speed of this particular section is going to be just plain 1.5 meters per second. And the plus you can ignore. You can put it if you want to. But anyway, speed, you don't care about the minus signs. You just throw an absolute value around the velocity, and you're answering the question really, how fast am I going? I don't care what direction. Just tell me how fast am I going, okay? So those are the basics that you need. 5 really important definitions. We went through a lot in a hurry. Bring your questions to class, and I look forward to seeing you there.